Hi everyone, welcome back to the channel. In this video, I will walk you through the design and a simulation of a high current, high voltage, multi-output power electronic converter. The system is supplied by a 415 volt 3-phase AC source and is capable of producing a multiple DC output, including a fixed, variable, isolated, and a series connected high voltage output reaching up to 2500 DC. I will cover the design approach, rectifier and transformer selection, control strategy, and simulation results using the MATLAB Simulink. Let's get started. Firstly, the system overview. The converter is designed to supply multiple industrial DC load from a 3-phase input from a 415 volt at 50 Hz AC source. The system delivers first output is a 1500 volt at the output terminal of O1 to O2, and it is capable of supplying a constant load of 12 kilowatt. Next, a variable DC output of 200 to 2000 volt, supplying a variable load of 0.25 kilowatt to 25 watt at the terminal O3 to O4 is required. And next is two independent, electrically isolated, producing 1200 volt. So it will be the terminal O5 and O6 and O7 to O8. This terminal should generate 1250 volt, and each terminal is connected to the constant load of 5 kilowatt. Now when they are connected in series, when these two rectifier circuits or converters are connected in series, it should be capable of producing 2500 volt, and it should be able to supply to the load of 15 kilowatt. Other key performance requirements are the voltage regulation should be within plus or minus 5%. Then low output ripple, it should be below 10%. Then it is saying that we need a galvanic isolation of O5 to O6 and O7 to O8, and tolerance of 200% momentary overload should be also considered. The resilience against 20% input voltage spike should be also considered in this project. Now moving forward, let's discuss on the design architecture. To meet these requirements efficiently, a modular converter architecture is used. So the system consists of two 3-phase step-up transformer. It consists of a combination of uncontrolled diode bridge and SCR-controlled rectifiers. Then dedicated transformer windings were given to achieve the galvanic isolation. This structure keeps the design more compact. It requires less number of components, and we try to optimize its efficiency and controllability. Now you can see that I have a 3 subsystem where the system source have a source where 3-phase source is used with 415 phase-to-phase voltage at a 50 Hertz frequency. Then it is given to the 3-phase VI measurement to collect the phase voltage and phase current and active and reactive power at the source, which is given at the display here. You can see that we are giving a 415 phase-to-phase voltage, 23 phase current of 23 amps, and the active power and reactive power is shown in the input. Now, the system 1 and system 2 consist of the rectifiers and converters. Then system 1 will produce the output O1 to O3. It produces O3 to O4 and O9 to O10. Then system 2 consists of two rectifier circuits. These two rectifier circuits, and it produces an output of O5 to O6, O7 to O8, and these two rectifiers are connected in series to produce O5 to O8. You can see that I'm using two sliders to control the rectifiers for O1 and not O1, O9 to O10 and O3 to O4. I will discuss in detail, and I'm using two switch to make these two rectifiers in series. The output waveforms are given here, where you have a DC voltage and average DC voltage and average DC current at the output. Now, moving on to the transformer design, let's firstly go into the transformer number 1. Each system consists of two transformer. Whole system consists of two transformer, and this is the transformer number 1. For the transformer number 1, it is serving the rectifier system 1, system 2, and the output 9 to output 10, terminal output 9 to 10. So it is serving 3 rectifiers currently, and the transformer 1, it supplies to the output 1, which will produce 1500 fixed voltage, and it will also supply to the bridge rectifier, which will produce a variable output of 200 to 2000 volt DC output. And in addition, output 9 and output 10 is also connected in parallel to the first secondary output of the transformer. However, this transformer 1 is a 3-winding transformer. This transformer have 3 winding, which are connected in star, and the core type is 3-limb core. Then you can see that The nominal power is 100 kVA, 100 kVA at a frequency of 50 Hz. The primary voltage is 415 at the primary side, and it is step up to first winding of 1111 volt, and second output terminal. This one will have an output of 1111, and this one will have an output of 1493. So we are using a transformer where we have 415 volt at incoming, and at the secondary side we are stepping up to 1100 and 1400 volts. The transformer's internal resistance and inductance are shown in here. Then I'm giving it to the three-phase via measurement to measure the active powers and other parameters you can get. So this is the transformer number 1. Transformer number 2 is in the system 2, where transformer number 2 is also a 3-winding unit. However, the transformer winding primary is connected in star, and two secondary windings are connected in delta. Now the nominal power is 60 kVA and the frequency is 50. Then at the primary we are giving again 415, and at the secondary both the terminals, two terminals from both secondary will generate or step up the voltage is step up to 936 volt, and it fits the system 3 and system 4, or output terminal 05 to 06 and 07 to 08. Then now why do we give two different transformer? So that we can isolate the outputs each secondary. This will ensure a full electrical isolation or galvanic isolation. These transformer ratings were selected by accounting the real power demand, harmonic distortions, displacement power factors, and we also consider 200% overload conditions. Let's move on to the rectifier topology. For the rectification, first rectifier for the system 1 is 3-phase fully 3-phase uncontrolled bridge rectifier with 6 numbers of diodes connected something like this. Then a 3-phase output terminal from the transformer is given to the each legs of the rectifier. This will generate a fixed of 1500 volt. And why do we choose the 3-phase uncontrolled bridge rectifier? Because it offers a high efficiency, it will produce a low ripple at the output, and excellent. This type of rectifier is excellent, have an excellent reliability for the constant DC load. Next, for the variable, system 1, we are connecting it to the load of 12 kilowatt load, and the average DC voltage and DC currents we will get from here. Next is the system 2. System 2, we have a load of 25 kilowatt, and this load is now connected to the this load is a variable load. You can change the load from how much you can change the load, and however this rectifier should uh, generate an output of 200 to 2000. So I'm using a universal bridge rectifier, which will represent a fully three-phase fully controlled SCR bridge rectifier. So this should be SCR bridge rectifier. Here is the terminal or the parameters. Then to control this rectifier, I am using a firing angle or the slider, which will change the firing angle from 0 to 85. At 0, it will produce 2000 volt at the output, and at 85-degree firing angle, it will produce 200 volt output for DC voltage. Then your slider is connected to this constant block, and we're giving it to the PWM generator. PWM generator is generating the firing angle, which is connected to the gate of the universal bridge. By controlling this gate, you will be able to get a variable DC output. Next, okay, in the system 2, we have two three-phase uncontrolled bridge rectifier. Similarly here, and this is I called it as a system 3 and system 4. However, the output terminal is 05 to 06 and 07 to 08. And they're using the three-phase bridge rectifier. This is connected to the transformer 2, and they are supposed to produce 1250 volt DC output individually. Therefore, they are connected to the load of 5 kilowatt load versus 5 kilowatt load respectively. However, when they are connected in series, it is connected to this 15 kilowatt load. Now, to make them in series, I'm using 4 different switches, ideal switches, and these switches will be controlled by the toggle switch. Now you can see that this switch and this switch. Firstly, let's make this circuit in series. You have the rectifier circuit from here, and output number 7. You will connect the output number 7 to the output number 8. So when you connect this one to this one, so it becomes a complete circuit. So series. Now they are connected. Two rectifiers are connected in a series, and this idle switch and this idle switch will be controlled by one toggle switch, and this idle switch and this idle switch will be controlled by another toggle switch. So you can see that we have two toggle switches, switch 1 and switch 2, and this switch 1 and switch 2 should be switched on alternatively to make the 05 and 05 to terminal 05 to 08 in series. Okay. By using this transformer number 2 and giving it to the separate source, different windings, separate windings, we guarantee a galvanic isolation and enhance the operational safety. Now, why did we use the power semiconductor? All the rectifier uses 600 volt rated power diodes and SCRs connected in series to withstand the maximum or the required peak inverse voltage. We are also considering 80% voltage deteriorating of the diodes and SCRs, which is applied to each device to ensure the safe operation under transient conditions. So therefore we are choosing the semiconductors or the diodes and the SCRs of 600 volt. Peak is 600 volt, right? PIV. So peak inverse voltage. Next, if I talk about the control strategy for SCR based rectifiers, asynchronized gate pulses are used to control the conduction. We're using the gate pulse to control the conduction, and using these sliders. At the firing angle, zero firing angle, maximum DC voltage is obtained. Then, by increasing the firing angle, it will reduce the average DC output. For example, at output 3, at zero firing angle, the output reaches 2000, and at 85, when we increase the firing angle to 85 degree, then the output drops to approximately 200 volt. Let's once simulate this model and see the output. While simulating, okay. Let's check the results with requirements from the question. It is saying the output terminal O1 to O2 should generate 1500 volt. So it is producing 1507 volt and 0.125 amps of current IDC. This is average current and average voltage. Then if you check the waveform, this is the output waveform where you have a current IDC of 0 point something here. You can firstly the waveform of the DC voltage. You can see that this is a DC voltage waveform, and the peak voltage is how much? 1179 volt, and you can see that its mean is 1507. And if you want to check for the current, let's see for the current. We have a peak of 1635 at time. In this millisecond we have 0.135 so this is a big current. Okay, moving to the next output, we have 85-degree firing angle. So 85-degree firing angle, it should produce 200 volt. DC voltage is 207.5 volt, little higher, and current is 1.289 voltage. Now let's change the firing angle to, let's say, 50. Then it should give the different output voltage, because this output terminal is a variable output. So what happens when we change the firing angle? Based on the PWM generated, it controls the SCR switching, and based on that SCR switching we get variable output, DC output. So at 50-degree firing angle, I'm getting output voltage DC voltage of 1268 with the current of 7.9. However, for this design, what is important is the maximum voltage, DC voltage it can produce, because it should serve the load of 12 kilowatt, and maximum load will be 12 kilowatt, right? So to serve that, if we go to keep our firing angle at 0, it should be able to produce 2000. You can see we are able to produce 2000 volt DC voltage, and its current is 12.5. So terminal 3 to 4 is a variable output. You can change from 85 to 2000. Next is terminal 9 and 10. I will talk about that later. Let's move on to the output voltage. Firstly, let's run the let's move on to the terminal output terminal 05 to 06 and 07 to 08. It should generate 1250 each, and to do that, let's make the switch in. We will keep the circuit independently without putting it into the series, and each rectifier should produce 1250 volt. Yeah, 1250 volt. Okay, we already got the output here. Output 5 and 6 is generating 1256, 1253 respectively. The current is 4.02 and 4.02. Now let's make them in series. To make them in series, I have to keep my switch 1 on and switch 2 off. And we are supposed to get an output voltage of, okay, we are connecting 15 kilowatt load, so therefore we need 2500 volt of this output voltage. So in series, yeah, it is giving 2500 output voltage. The waveforms are all same in as shown in the above. We have checked earlier. And if I talk about output 9 and 10, this output 9 and 10, I have two different model. Number one, I'm using SCR-controlled rectifier, and I can also use a buck boost converter. I mean, the buck converter to this, where I am getting, I require the output voltage of, for output 10, 9 to, for output terminal 9 to 10, this is a full bridge controlled rectifier, and we are using a buck converter. It serves the same purpose, but you can just have to be connected in a different terminal. If you are using the three-phase control bridge rectifier, then you can connect it in parallel to the system 1 of the transformer winding 1, transformer 1's winding 1, and you have a 10 kilowatt load connected, and you are using a capacitor of how much, 180 e to the power minus 6 farad, and a freewheeling diode is used. This capacitor will reduce the, helps in keeping the ripple factor less than 5%, and the output at this terminal should be a variable of from 0 to 1500 volt. You can know that this is also producing 1500 volt. Output 1 is also producing 1500 volt. So to make it variable, you can also use a buck converter, and by changing the duty cycle from here and using this buck converter, you can also do the same. You can serve the same load, where your buck converter should be connected to the output of a system 1. And if you are using the buck converter, you have to use IGBT. A diode is connected like that, and a detailed video on the buck converter is in my channel. You can go through it. I'm not going to explain it here. So what are the important informations that I have to think? Yep, we have our Simulink results almost there. However, you can see that there is inconsistency in, or we did not get a perfect output voltage. Some output voltage are higher, some output voltage are lesser. This can be because of this precisions is deteriorated due to the voltage drop caused by the transformers that we're using, and even the power diodes and SCRs that we are using. So this design highlights an important trade-off in the power electronics, where your diode rectifier offers a very high efficiency and simplicity, but you can say that this cannot be controlled. Since the diode cannot be controlled, you can't make your output variable. However, if you want to have a variable output, we need to use SCR rectifier, and it will provide a voltage regulation at the output, and this will increase the cost of your circuit, and it will also increase the losses due to the firing angle. By combining both approaches, the system we could achieve is of a high efficiency, and we could get more precise regulation. In summary, I would say that this project is a robust multi-output. We have a very high voltage DC power supply, and this can be applicable in many industrial uses. So thank you for watching. If you found this walkthrough helpful, please feel free to like the video and subscribe for more similar videos. I'm going to upload the MATLAB file or Simulink file in the Gumroad. You can check my bio and the video description. I'm going to give you a link, and you can download the MATLAB Simulink file and use it in your project. Thank you for watching. We'll see you next time.